Hey, hello. Welcome to class this wonderful rainy Friday where I'm sure you all thought that you weren't going to be able to do anything, but no, we have class today. We have assignments today. So I assume if you're watching this video that you've already gotten on Google Classroom. Make sure that you check on Google Classroom every single day, check on Discovery Education every single day, and see what the assignment is. As long as we are out on remote learning, we should have one assignment at least that you need to complete every single day. Today's will be pretty easy, but it comes along with the lecture, so let's go ahead and get into it. Today we are starting on the Earth's interior. So that is what the constructed response is. You're going to have to answer a couple questions, type out a couple answers, and then you should be done with my class for today. So make sure you get on Discovery Education and follow along with this video, and you should be able to complete the assignment pretty easily. So I just want to start with a short lecture where I go through some of the things that they're talking about and kind of introduce the Earth's interior and its different layers and its structure, which is what the entire section is about. So you can see here we have the Earth's interior, and I've assigned this reading for you to be able to get to it very easily and kind of get to the answers pretty quickly. So they start off by basically saying, visitors to volcanic locations like Hawaii and Iceland find themselves mesmerized by the glowing, roiling lava flows. What is lava? Where does it come from? Why does it erupt onto the Earth's surface in certain places? And so we're going to kind of go through that a little bit. I mean, we obviously know what lava is. Where does it come from? It comes from below the ground in the superheated parts of the Earth. And why does it erupt onto the Earth's surface in certain places? Because there's pressure behind it and there's holes in the ground, and that allows it to kind of come to the surface. So really quickly, I might talk over it a little bit. Hopefully YouTube doesn't take my video down. But we have a nice
of small earthquakes here.
Bill Nye video that he's talking about here.
It was a signal that the long dormant volcano was waking up.
He's talking about Mount St. Helens.
May 18th, it did.
On the Mount St. Helens eruption. We may have already watched part of this video before, but he's kind of going through this.
500 times the atomic bomb that was dropped on Hiroshima. A cloud of hot ash roared 15 miles into the atmosphere. "230 square miles of forest were wiped out. 6 million trees, enough wood to build 300,000 two-story houses." Throughout recorded history, civilization has lived with the threat of earthquakes and volcanoes. But the cause of their destructive power remained elusive, shrouded in mystery. It wasn't until our first great discovery that a picture of what was happening inside the Earth began to emerge.
So he's just kind of setting up the idea that volcanoes and earthquakes help us peer inside the Earth. And one of the things that they have that lets us do that is seismic waves or shock waves. So when a large explosion happens or when an earthquake releases its energy, they release waves out through the Earth that travel through all the different layers. And if we're able to know two things: A, when those waves were created, when the earthquake happened or when the volcano erupted, and B, we're able to record those waves somewhere else on the Earth, we can do math to try to figure out where they've gone and where they've been and how fast they traveled, which tells us a lot about the subsurface. And so looking at seismic waves is a very useful tool that we discovered. Let's see what this next video is about real quick.
You can learn a lot about the world by looking at a globe. It shows the continents, the oceans, the locations of mountains and other landforms. But a globe can show you only what's on the surface of our planet. Have you ever wondered, what's inside the Earth? Nobody has ever been to the center of the Earth, so how do we know what's there? If you bounce a ball while standing, the ball will return in about a half a second. But if you kneel down, the ball returns much more quickly. You can figure how close you are to the floor just by measuring the time it takes for the ball to return. This is the same principle scientists use to determine what's inside the Earth. But they don't use balls, they use explosives. When an explosion is set off near the Earth's surface, it creates shock waves that move toward the center of the Earth. When the waves strike certain objects, the waves bounce off, returning to the Earth's surface, where they cause vibrations which can be measured by machines like this. By studying these vibrations, scientists are able to learn a lot about the materials that make up the interior of our planet.
Yes, so the whole point of that is we use these seismic waves, these sound waves that travel through the Earth's surface when we have an explosion, when we have a large explosion like a volcano erupting or like an earthquake going off. That's going to send down waves. The waves go down into the Earth, and then at some point in time, they encounter something that makes them reflect back. The longer the time frame in between when the wave was started and when it reflects back, the further down it went. The same as the kid with the basketball. The higher up he's bouncing the basketball, the longer it takes for it to go all the way down and all the way back up. But as he got lower and lower in his dribble and was dribbling just like maybe a foot off the ground, the ball was going down and coming back up very, very quickly. And so we use those times to figure out what the surface or the subsurface features are in the Earth. And so the amount of time it takes to go down and back is the amount of time or equal to the distance down inside the Earth those features are.
Wave is the P wave or primary wave.
So these are different types of waves that we get as we try to look through the surface. P it doesn't always, but it can stand for primary, meaning it's the first wave to arrive. It's the fastest wave to get here. So they're going to go through some of the other waves. There's a P wave, there's S wave, and then there's surface waves, and they should go through all three, I think.
As it moves, it pushes and pulls the rock, just like sound waves push and pull the air. The second type of body wave is the S wave, or secondary wave. S waves shake the Earth up and down and from side to side, perpendicular to the direction the wave is moving. P waves can move across the diameter of the Earth, but S waves cannot. This tells geologists that deep in the Earth there is a layer of liquid. By observing waves as they travel through the Earth, they can work out how deep this liquid layer is. They can do the same for the different parts of the Earth, like the mantle and the crust. In essence, seismography provides a roadmap for geophysicists, engineers, and environmental scientists who want to know what lies below.
So essentially, this works the same as us figuring out how deep the ocean is. We send sound waves down. The longer they take to go all the way down and bounce back, the more shallow that feature is. And so in the same way we use sonar to bounce off the ocean floor and come back up to figure out the depth of the ocean, we can do the same thing inside the Earth. We make sound waves. They go down. They bounce off of different layers like the Earth's crust or the mantle or the core. And when they come back up, we can do a little bit of math to try to figure out where they're at. So we're going to start to go through the different layers. The first layer they start with is the Earth's crust. And just like a pie crust, the crust is going to be the hard shell on the outside. All the rocks are solid because they're at a cool temperature. Today, the temperature outside is like in the 60s, I think, not too bad. And so at 60 degrees Fahrenheit, there aren't going to be any melted rocks unless they just came to the surface and haven't had a chance to cool down yet. But all the rocks at the surface are going to be solid. And so the crust is a nice solid rocky layer on the very outside of the Earth. And that's where we live. That's where all the water is. It's where all the plants are. The entire surface of the Earth is covered with crust. Now, there are two different types of crust. We have oceanic crust and continental crust. And we will get into this also when we get into plate tectonics. There are oceanic plates and continental plates. But they are what they sound like they are. The continents are made of continental crust. The ocean bottom below the water is made of oceanic crust. And they are slightly different. The continents are a little bit less dense. The oceanic crust are a little bit more dense, so it's heavier rock, even though they're thinner layers. They kind of have a picture of this right here. You can see the continents are relatively thick. The oceanic crust is relatively thin, and they all kind of sit on top of the next layer of the Earth, which is the mantle. The mantle is just below the crust. So they give you a little bit of detail about the crust, the mantle that it's on top of, and also they introduced the term lithosphere. Litho meaning rock, and sphere meaning the outside sphere. So the lithosphere is the very outside surface, all the rocks that we interact with, that we live on, that we grow our food on, and all that jazz. So they talk about some elements that are in the crust: oxygen, silicon, aluminum, iron, calcium, magnesium, sodium. All of these elements are towards the upper surface of the Earth and the crust. And I'll point out that most of these are pretty light elements. Oxygen and aluminum and silicon are all relatively light compared to some of the heavier elements that are going to be in the mantle and the core, like iron and nickel. There is some iron at the surface. It's just not the major portion of what's at the surface. Most of the surface rocks are made of oxygen and silicon, which are a lot lighter in weight than iron and magnesium and something like nickel. So the two types of crust, as they say, differ in density. The continental crust is less dense or lighter. Your oceanic crust is more dense and heavier. It contains more iron and more magnesium. And when they come together, the continents will stay up higher. They will float essentially on top of the oceanic crust. And so if they smash together, the oceanic crust gets pushed down because it's a lot heavier, a lot more dense than the continental crust. But we will get to that when we get to plate tectonics. So they talk about the formation of the Earth. And basically, as the Earth formed and started to cool, in its very young stages, it was all molten and pretty mixed up. But over the next few billion years, as it slowly cooled, your heavier elements sank towards the bottom. And so the elements that are in the core of the Earth, iron and nickel, are going to generally be heavier than the mixture of the elements that are higher and higher up. And so your core, iron and nickel, is more dense than your mantle, which has a couple other elements mixed in: magnesium, sodium, different elements like that. And then as you go up to the crust, you get more oxygen, more silicon, less and less dense rocks. And so each layer of the Earth, in essence, kind of floats on top of the layer below it. Did they talk about the mantle at all? They just went through Earth's crust. Then they go to Earth's core. We know now by looking at the waves that pass through the Earth that there are two layers of the core. There's an inner core and an outer core. You can put them together and just call them the core. But technically, there's an outer core that acts as a liquid. It's hot enough to be completely melted. It acts and works like a liquid. The inner core does not act like a liquid. It acts like a solid. And the reason here is the melting temperature is well beyond where it should be melted, but the pressure holds everything together and keeps it from being a liquid. It acts as a solid. Both the inner core and the outer core are made mostly of iron and nickel, but know that they work a little bit differently, with the outer core being more liquid and the inner core acting as a solid. Then they go ahead and talk about the mantle. The mantle is going to be in between the cores and the crust. So you have the crust on the outside, the core on the inside, and the mantle is going to be what separates those two. This is the largest layer. It takes up the most mass. They say about 2/3 of the Earth's mass. And the mantle is what feeds the lava or magma that eventually comes to the surface in the form of volcanoes. So the mantle is very thick. There's a lot we still don't know about the mantle, how it moves. Convection is going to be the way that it moves, but we still argue about exactly how those convection cycles happen. But you all have learned about convection before. Convection is the idea that hot things will rise and cool things will sink. So if you have the core of the Earth, which is much hotter, the core is going to be heating up this material, and the stuff that's near the core is going to rise up because it's now hotter and less dense. And so it's going to rise up to the surface, and your cold stuff that was just up near the surface that is cooled down a little bit is going to sink down. And so we have these large convection cycles that rise and fall, just like hot liquid in a coffee cup. As it cools and gets heated by the cup, it's going to form this kind of convection cycle. So we've learned about that before. That's not a new concept, but it works in large scale inside the Earth. And so we've kind of gone over the reading already. Let's take a look at the assignment. Only 2 questions today. So question number 1, describe the chemical and physical properties of each of Earth's compositional layers. So we have those 3, the crust, the mantle, and the core. You need to tell me what elements it has in it. That's the chemical properties. And what state it's in. That's the physical properties. Is it a solid? Is it a liquid? Is it a gas? How's that going to work out? So just to go back real quick, the core, the mantle, and the crust. You can see here that the crust is going to be solid. They talk about a couple different layers of the crust. You can mention oceanic and continental crust. Give me these elements. That's going to be your chemical composition of the crust. And you've already mentioned that it's solid. And out of those 3 layers, the crust, the mantle, and the core, the crust will be the coldest because they ask about thermal properties in this question as well. So tell me that this layer has the least amount of heat. It's cooled down the most, which is why all the rocks are solid. Then the mantle, they talk about the mantle and the thickness of this. Know that the mantle acts like a solid. Waves travel through it like a solid. We know that it's a solid. It's just more like a soft solid. It says its consistency is like putty and it flows slowly over time. So it can move around and have those convection cycles, but it is a solid. It's not a liquid inside the mantle. And then they want to know a little bit about its chemistry. Let's see if they give us any elements inside the mantle. Yes, the composition of the rock in both layers of the mantle is similar, consisting mainly of iron and magnesium-rich minerals. So mostly iron and magnesium, along with some other minerals in there. And then we go to the core. Right here they talk about the core. You need to talk about the inner core and the outer core. The outer core being a liquid. The outer core acts as a liquid. The inner core acts as a solid. And what kind of elements are they made up of? They're made up of iron and nickel. Both the inner core and the outer core are mostly iron and nickel. The outer core probably weighs a little bit less, or is a little bit less dense, but they are both mostly iron and nickel. Now, the last thing to ask about on this first question is thermal properties of the layers. Tell me about the temperatures. The heat is going to increase as you go down into the earth. So the crust will be the least hot layer. Then the mantle gets a little bit hotter. The outer core gets a little bit hotter. And the inner core is going to be the hottest place inside the earth. And so thermal properties are just going to get hotter and hotter and hotter as you go down. Now, second question. Earth's interior may also be divided into structural layers. Distinguish between the lithosphere and the asthenosphere and the mesosphere, and what makes up tectonic plates and what causes them to move. So this one's a little bit more complicated. The lithosphere, as they say right here, is going to be a brittle part of the Earth and its crust. So this is the part that we live on, the very top, your oceanic crust, your continental crust. The lithosphere is what's broken up into your large tectonic plates. Now, let's see where they talk about asthenosphere. The asthenosphere is going to be a molten layer. And let's see, do they talk about it here or do they talk about it in the mantle? Maybe in the mantle. Come down here to the mantle. Yes. So they talk about the asthenosphere and the mantle. The asthenosphere is a semi-molten layer. So it's almost melted, but it's not really melted. It acts like a thick plastic or like a really thick honey layer. But in essence, when we talk about plate tectonics and you wonder how can like the United States or all of North America How can North America just slide around on the Earth's surface and move from one place to the other, like plate tectonics tells us that it does? The asthenosphere is that answer. The asthenosphere acts as like a slip and slide to allow these large continents to move around and go from place to place and be able to change their location, despite the fact that they're super large and weigh an immense amount of weight. They're still allowed to move. And so the asthenosphere is just underneath the lithosphere. It's soft like putty and flows over time and allows things to move around. And then they talk about the mesosphere. Somewhere in here, they talk about the mesosphere. The mesosphere is essentially just going to be the rest of your mantle. Meso means middle. And so the middle part of your mantle, the rest of your mantle, all the way down to the outside of the core, is going to be the mesosphere. It's a thick, kind of almost melted rock. It allows for movement. That's where your convection cycles happen. But it's not really part of the crust anymore. It's all the rest of the mantle. So the crust is going to be your lithosphere. The mantle is going to be divided into your asthenosphere and your mesosphere, which is in the middle. And so going down from the surface, you go lithosphere, asthenosphere, mesosphere. So give me just a little bit on each of those. And then the last part of the question is, let me scroll down. Last part of the question, what makes up tectonic plates? Oceanic crust and continental crust make up tectonic plates. So the lithosphere and those two different parts of the lithosphere, oceanic crust, continental crust, make up your tectonic plates. What causes them to move? We'll get into this later in the section, but essentially the convection cycles and the asthenosphere. So convection in the mantle and the asthenosphere allow them to move around on the Earth's surface and change their place, which is what we observe through satellite imagery. So we can see the plate tectonics moving. We know that it happens. We experience earthquakes because of it and have volcanoes because of it. So I hope that I've answered all your questions today. If you have any questions or need any help, please just email me and I will respond to you through email and help you get set up. But 2 short answer questions today. Give me a couple sentences for each of these. What is the crust, the mantle, and the core? How do their temperature changes happen from top to bottom? What's the difference between the lithosphere, asthenosphere, and mesosphere? And what makes up tectonic plates and what causes them to move? You have this video. You also have the reading, which I have assigned, so you should be able to get to that. Type me up some answers and submit it to me, and you'll be done for the day. So if you see this, just make sure that you are getting on the Google Classroom every day and checking your assignments. Check out Discovery Education also. You can see the empty classroom behind me. So I am here at work. And if you have any questions, please do let me know. Have a good weekend, and I'll see you Monday.